Hey, this is Avi Gutman with another Ask Me Anything event brought to you by quantreasoning.com. I invite you to join me live next time. We do this every Saturday at 11 a.m. Eastern, and you can attend for free by starting your free trial at quantreasoning.com. So I'd like to walk you all through some of the observations that I make as I read this question. My first observation is at the end of the first sentence. The observation there is that 336 must be the product of hourly rate multiplied by number of hours. So we're looking at some kind of product of two factors. The second observation I make is that everything on the slide, they're all integers. We've got 4 hours longer, so 4 is an integer. $2 per hour less, 2 is an integer as well. 336, of course, is an integer. And all the answer choices are also integers. Now, does this guarantee that the hourly rate is an integer? No, there's no guarantee that the hourly rate is an integer. However, if I end up solving this and finding out that the hourly rate is not an integer, I would be beyond shocked. Everything I know about the GMAT and seeing all these integers on the slide, it's almost guaranteed. I would even say it is guaranteed that everything here is integers. And if I'm going to go ahead and make that assumption that we're only dealing with integers, then it's probably a good idea to find the prime box of 336, since that number is presented here as the product of two different pairs of factors. The first pair of factors would be his regular hourly rate times his estimated number of hours. That's a pair of factors that produces 336. And separately, there's apparently another pair of factors that produces 336. And this pair of factors has numbers, one of which is 4 more than its partner in the first product, and the other is 2 less than its partner in the first product. So when we're looking at two different factor pairs that both produce 336, I think that finding the prime box of 336 will be useful. Now, when I look at the number 336 and I want to factor it down, I can't help but notice that 300 is a multiple of 6 and 36 is also a multiple of 6. And the reason I notice that is because I think of the number 336 as 300 plus 36. That's how I think about it. Another way to think about that number is 400 minus 64. So because I don't use long multiplication and long division and long addition and long subtraction, I'm always estimating numbers and thinking of them that way, like finding a friendly round number in the area and then seeing by how much we're offset from that number. So I think of it as either 300 plus 36, each of which is a multiple of 6. So then I could say, well, if I take out a factor of 6, I'd be left with 300 over 6, which is 50, plus 36 over 6, which is 6. So it's 6 times 56. So I found that factor pair fairly quickly that way. Or if I think of it as 400 minus 64, I can't help but notice that both of those are perfect squares. So we have the difference of squares here. And with the difference of squares, we could rewrite it as 20 squared minus 8 squared. And that's going to be 20 minus 8 times 20 plus 8. So that's the special product for difference of squares. So that would be 12 times 28. Now, I don't think there's one of these approaches is better than the other. I think they're both fine. But either way, we're trying to get to the bottom of the factor trees to find the prime box. So this would be a 2 times 3, and this would be, I guess that's 2 times 28. And 28 is 2 squared times 7. So these are all the primes. Or if you did it this way, it would be 2 squared times 3 and 2 squared times 7. So either way you do it, you should end up with the same prime box, which would have a total of 4 2s, a 3, and a 7. Then what I would do is find the prime box of each of the answer choices. And as I look at the answer choices, I'm not just interested in the answer choice itself, I'm also interested in 4 above the answer choice. So if the estimated time for the job was 28, then the job would have actually taken 32 hours. If the estimated time was 24, the job would actually take 28 hours, and so on. So I'm adding 4 to each of these, and then I'm going to prime box these 10 numbers, essentially. And what I'm looking for is what would be the other factor. Like if each of these is a factor of 336, what would be the partner? And how will I quickly find the partner? By looking at the prime box of 336, which we said was 2 to the power of 4, 3 to the power of 1, 7 to the power of 1. Now, some of these 10 numbers I can just see are not going to be factors. 32 jumps out at me because 32 is 2 to the power of 5. And I don't have 5 2's, I only have 4 2's in the prime box of 336. So that eliminates A. What else can we eliminate here? 20 has a 5 in it. Do you see any 5's in the prime box of 336? No. So C is gone. 18 has 2 3's in it, right? There's a 3 squared in the prime box of 18, so D is gone. So we don't actually have to find all the prime boxes of all these numbers. We can save some time. And I want you all to ask yourselves, how quickly would you have been able to get this far? Because I think that if you don't regularly practice prime boxing, finding the prime box of 336 can take a long time. If it's not an activity that you do daily for a few weeks, it could take you the full 2 minutes just to find the prime box of 336. And if that describes you, then I strongly encourage you to make this a daily habit to practice prime boxing. Because you want something like that to take no more than 20 seconds, finding the prime box of 336. And I want you also, when you are practicing prime boxing, to have some fun with it, to play with it. You see, in this case, I thought of 2 different and cool ways to start breaking down the number 336. And by doing so, I improved my skill with regards to this particular special product of difference of squares. What a wasted opportunity would it have been to only break down 336 in this one way. So the goal when you're practicing prime boxing at home is not to find the prime box as quickly as possible. Don't time yourself. That's not the goal. The goal is to have fun with it and to improve your number sense and flexibility with handling numbers. That's the goal. And as a side effect, you will become much, much quicker at prime boxing. We had B and E remaining. So B, 24 versus 28. The prime box of 24 would be 2 cubed, 3 to the 1. And if I put the prime box of 336 here at the top, just to remind ourselves what that was, I believe that's what it was. If you take 2 cubed and 3 to the 1 out of it, you would still need a 2 to the 1, 7 to the 1. That would be the leftover. Do you see how I'm doing that? I'm comparing the prime box of 24 to the prime box of 336, and I'm wondering, well, what are the remaining primes that haven't been accounted for yet? Now, 2 to the 1, 7 to the 1, that's 14. So this is a very quick way to discover that 336 divided by 24 is 14. I mean, I don't know how else I would have done it. I mean, I don't use long division. So I guess I would have had to break down 336 to 240 plus 96, then divide 240 by 24 and 96 by 24. So I could have done it that way. But I can save a lot of time by having the prime boxes. Now 28, that would be 2 squared, 7 to the 1. And what would remain inside the prime box of 336? What's still unaccounted for? 2 squared, 3 to the 1, which is 12. And I don't even need to check E, because this already works, right? The difference between 14 and 12 is 2, just like the question said it would be. So now I can pick B and move on to the next question. Now, as usual, my concern isn't so much with solving this particular question. My concern is with learning a strategy from this question to be applied in other questions And I would say that the strategy is it's fairly safe to assume that the factors are going to be integers when everything that you're seeing is integers. And if that's the case, then you can use prime boxes to save a bunch of time. But I'm hoping that this also helped you see the usefulness of prime boxes. And just to illustrate this further, if we need to divide 336 by 28, we can do so using the prime boxes. So it would be 2 to the 4, 3 to the 1, 7 to the 1, over 2 squared, 7 to the 1. And then you can reduce the 7s, reduce 2 of the 2's. You'd be left with 2 2's at the top. So you have 2 squared times 3 is 12. So that's how that works. And I believe that this also improves our conceptual understanding of divisibility. Hey, I'm just going to interrupt my own video for a moment here. If you're finding value in this video, please let me know in the comments below. And give this video a thumbs up. It really motivates me to keep uploading a new video every day. Alright, back to the video. I suspect that this is a pretty hard question, but I wonder if any of you wants to give it a try and talk us through your reasoning. If these both said 5, and this also said 5, then you can apply that formula. If the remainder of a number when dividing by 5 is 1, and the remainder of another number when dividing by 5 is 1, then when you divide their product by 5, your remainder would be 1 times 1. And that was something we discovered, I proved it algebraically last week. But here the divisors are different, and not only are they different, they have no common factor between them. I mean, if they were 5 and 10, well, then maybe I could still do something, because 5 and 10 are, like, they overlap, right? Every other multiple of 5 is a multiple of 10, so there's a very serious overlap there on the number line. But with divisibility by 5 and divisibility by 3, I mean, those are separate prime numbers. Their cyclicality on the number line has nothing to do with one another. So conceptually, that's why I would immediately pick E, just because we're talking about distinct worlds of divisibility that have no overlap between them. They have nothing to do with each other. So that's conceptually. Now, if I wanted to be a bit more confident and kind of prove to myself that the correct answer is E, I would have inferred from statement 1 that P plus N isn't divisible by 5. Does everybody agree?
Yes.
Is that a fair inference?
Yes.
That's true, right? It's not a multiple of 5. We know that. Is it a multiple of 3? I'm asking for a friend. Is P plus N a multiple of 3 according to statement 1? I don't know. No idea. Maybe, maybe not. You'll see in a minute why I'm asking that. From statement 2, what can I infer? P minus N isn't divisible by 3. Do you agree with that?
Yes.
But is P minus N divisible by 5?
We don't know.
Don't know. Does anyone see where I'm going with this? Like why I'm asking those questions? If the answers were yes, so think through this together with me. If P plus N is divisible by 3, and P minus N is divisible by 5, because it's possible that they are, we don't know. Right? We don't know the status of the divisibility by those factors. If they are both divisible, then JD, what would you say about the product?
If P plus N is divisible by 3?
Yes, and P minus N is divisible by 5, then is their product divisible by 15?
I think yes.
Yeah, and then the remainder would be 0 when you divide it by 15. And if they're not, or even if one of them isn't, then the remainder would not be 0 when you're dividing by 15. So I think that's a beautiful way to prove to yourself conceptually that even when you combine the statements, you can't answer the question, because the question wants to know specifically what would be the remainder when you divide the product by 15. And I'm saying, not only can I not tell what the remainder would be, I can't even tell whether it would be 0 or not 0. Like I can't even say whether the product would or would not be divisible by 15. It's possible that the first factor isn't divisible by 5, but is divisible by 3. And the second factor is not divisible by 3, but is divisible by 5, and then the product would be divisible by 15 because you're getting the factors of 3 and 5 that you needed to get. You just got them from the opposite places. So let's draw a quick grid. Multiple of 5, multiple of 3, p plus n, p minus n. This would be divisibility dividing by 15 of p squared minus n squared, remainder. So if this is, and what do we know? We know from statement 1 that p plus n is not, and so that's from statement 1. We know from statement 2 that this is no. But if both of these are yes, that would lead to 0. And otherwise, so let's say else, not 0. Some other number, some other remainder. And that's how I proved insufficiency conceptually. Now, I'm going to make a claim here, and I'm very curious to hear your thoughts about this claim. I believe that this particular problem was written in order to test whether we understand conceptually that being given information about these two separate worlds of divisibility can't possibly be sufficient for us to answer about this world of divisibility. And that if we don't conceptually understand that, then we're very unlikely to be able to solve this correctly in under 2 minutes. And we are very likely to go over 2 minutes and maybe get it right, maybe not. That's why I believe this was written. And I'll also make the claim that if we do understand conceptually this idea of divisibility and remainders, then we don't need pen and paper and we can pick E in a matter of seconds. If we understand that these separate, distinct worlds of divisibility can't possibly allow us to infer anything about this world of divisibility. Those are my two claims. What do people think? Agree, disagree? But you see how, does everybody see how they designed this question? I mean, just notice that this divisor in the question stem just so happens to be the product of these two divisors. So they're really playing on people's misapplication of memorized rules. And I think a lot of people would say, oh, this really feels like a C, right? Because if you multiply these, and it just so happens that the product of these divisors is this divisor, C, right? So you can see how they design it that way. And I drew here a tick mark on the left to represent a multiple of 15. And then you can kind of see as you move to the right from there and looking at what's a multiple of 3, what's a multiple of 5, there's really no rhyme or reason or any pattern to go with there, right? Because, I mean, just to continue this a little bit further, so 3 units later you'd get another multiple of 3, and then another just 1 unit after that comes the next multiple of 5. And when you look for a pattern among the multiples of 3 and multiples of 5 in the context of multiples of 15, it just looks like a mess, right? You've got 3, 2, 1, 3, 1, and so on, and it's just going to keep changing. There's no pattern. There's no cyclicality. And the reason there's no cyclicality is because 5 and 3 are distinct prime numbers. Just to clarify it a bit further, maybe I would say the following. Looking at my number line here, if I were to ask you, is p plus n a multiple of 3? You could say, well, if this is p plus n, it could be, right? 1 unit to the right of a multiple of 15 could be p plus n. Then it's obviously not a multiple of 3 because it's 1 to the right of a multiple of 15, which happens to also be a multiple of 3. But if this here is p plus n, which it could be because it's 1 unit to the right of a multiple of 5, then it is a multiple of 3. So you can kind of see easily visually there that I don't know what the divisibility of p plus n looks like in the world of divisibility by 3. And the same goes for p minus n in the world of divisibility by 5. I just have no context and no information on that. And what this all reminds me of is something that I heard a lot in private tutoring with students over the years. I'm going to try to recreate for you the conversation that I would have with a student. And I think you'll see how this relates to the data sufficiency problem we just saw. we'd be looking at a GMAT problem, and there'd be a statement, let's say in data sufficiency. And the statement says, positive integer n is not a multiple of 7. And I would ask the student, okay, so what does that tell you? And often the student would say something like, well, if n is not divisible by 7, then it must be even. Or the student would say, well, if n is not divisible by 7, then it must be odd. And even and odd only have a meaning in the context of divisibility by 2. But the divisor 2 and the divisor 7 have nothing in common. So knowing the remainder of a number when dividing it by 7 can't shed any light whatsoever on the divisibility of that number in the context of divisibility by 2, and vice versa, right? If I told you some number is even, can you tell whether it's divisible by 7 or not? What if I told you that a number is odd? Then can you tell whether it's divisible by 7 or not? No, they have nothing in common. You can't make inferences from one world of divisibility to another world of divisibility unless the divisors have something in common. So I'll give you an example of divisors that have something in common. If I tell you that n is a multiple of 4, then you can infer that it's even. How come? Why can you make an inference there? Because 2 is a factor of 4. There's a common factor of 2 in those divisors. If I tell you that dividing n by 2 gives a remainder of 1, which is just a fancy way of saying n is odd, you could infer that in the world of divisibility by 4, the remainder would be either 1 or 3. In other words, you can exclude 0 and 2 as possible remainders when you know that an odd number is being divided by 4. Why is it that you can make any inference whatsoever? Because there's a common factor between those divisors of 2 and 4. But with divisors that don't have a common factor, for example 2 and 7, you can't make any inference from one to the other. Knowing the remainder when dividing n by 7 doesn't do anything for me in terms of finding the remainder when dividing by 2, and vice versa. So I think that people often jump to some kind of conclusion about whether a number is even or odd without having any justification. Right? And I'm sure you've also either thought it or heard somebody else think it, that if a number is a multiple of 3, then it must be odd. Or if a number is odd, it has to be a multiple of 3, or something along those lines. But understanding that there's absolutely no way to make any inferences from one to the other, I think would allow you, on a question like this, to pretty quickly pick E. Because we have 2 worlds of divisibility. Actually, we have 3 worlds of divisibility, if you include the 15. But these 2 have absolutely nothing in common. Now, they do each have something in common with the 15, but we're talking about the product of 2 numbers, one of which we have information in this world and one of which we have information in this world. But knowing about p plus n in this world doesn't tell me what p plus n looks like in this world, and vice versa for the p minus n. And that was my conceptual way of seeing that you can't solve the question, even when you combine the statements. Because again, divisibility by 3, remainder question mark for statement 1. Divisibility by 5, remainder question mark for statement 2. So when you multiply them together, so you've got something that you know in the world of divisibility by 3 is remainder question mark. And now you do know the divisibility by 5 remainder 1. You know that, but you don't know anything about divisibility by 3. So that's p plus n. And then p minus n, you know in the world of divisibility by 3 that it's remainder 1, and you know in the world of divisibility by 5 it's remainder question mark. And then you're asking for the product. You know for the product that what's going to be the remainder in the world of divisibility by 15? I don't know because of this question mark and this question mark. I'm going to have to say question mark. Yeah, a colleague of mine at Manhattan Prep said the solutions in the official guide are not solutions. They're a mathematical defense of the correct answer. It's not an explanation. It's certainly not a solution. It's a defense of the correct answer, a mathematical defense of the correct answer. And it's so true. It's so true because you're right. I mean, most of those solutions can't be done in 2 minutes because they're not GMAT solutions. And you have to remember that the goal of the official guide is not to help you do well on the test. That would actually defeat their purpose. I mean, the better people become at taking this test, the harder a job the test creators have, because their whole task is to take a population of candidates and split them into different scores, right? And rank them, essentially. And so it wouldn't make any sense for them to attempt to help the candidates do better on the test, because that just makes their job even harder. So I agree with you. I think the solutions in the official guide are worse than useless. They'll actually push your score down. And I've seen that happen to a lot of students. With regards to your concern about having a long way to go and maybe feeling a little bit demotivated as a result of seeing the creativity of actual solutions, I think that based on what I've seen with students over the years, a big part of it is changing the mindset. I think a lot of the creativity you actually do already have, but you're not in the habit of using it. And that's a result of being overeducated, because unfortunately the way the education system is set up is to destroy any creativity that children going into the system have. I see that now with my 6-year-old. He was born creative and he was very creative, and the more he's educated, the less of that spark of creativity I see with him, because he's told, this is how you must do it. And then he drills it 20 times and then all the creativity goes out the window. But it can come back because it was there to begin with. And what I've seen with students is there's almost like a click at some point after enough exposure to these creative solutions. They realize at a certain point that when a new question pops up on the screen, rather than try to fit some memorized procedure or algebraic solution that they've seen to this problem and kind of try to shove it in whether it fits or not, they take a deep breath, they lean back in the chair, and they just try to have fun with it and think outside of the box. Like, okay, it's a brand new question. I've never seen anything like it in my life. How would I approach such a thing? And I think at first that causes anxiety because your whole education has prepared you for trying to fit something into a prefabricated approach. So it can definitely increase anxiety at first, but I think with practice and once you start having fun with it, you realize actually this is a much more engaging and fun way to do these questions. And it also gives you the requisite humility to let go of questions when appropriate. Because you go, well, for this question, I mean, I'm thinking clearly and calmly. I'm not in a state of panic, trying my best, and it's, for whatever reason, it's going over my head. Okay, I'll just guess and move on to the next question. And that's absolutely necessary on the GMAT because it's an adaptive test. And that's something that's a lot harder to do when you come with all these prefabricated approaches and you try to fit them with force. So I think that should give you some reason for optimism, because it will at some point just click when you change your mindset and your habits and you approach each question as a brand new riddle to be solved the way that you would on trivia night at a bar or something like that. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.